Hello, people. Today I would like to make a video on the calculus of variations, referring to the text by Gelfand and Fomin. So first of all, I would like to talk briefly about myself and also the reason why I'm making this video. Uh, so first of all, this is the first time I'm uploading any YouTube videos. I'm a UCSC student, currently junior and soon senior. I entered as a physics student and I started doing math uh, on my second year. And the reason why I want to make a video on calculus of variations is that when I first did the subject classical mechanics, I find their approach to be pretty hand wavy, and which I don't quite like as a math student. And I find this book by Gelfand to be just right. So it's pretty rigorous, but at the same time, you don't need uh, a lot of familiarity with higher level subjects like measure theory or real analysis. So to read this text, you only need some basic mathematical analysis skills. So basic theories in integration and differentiation would be sufficient. So I'm planning to make more of these videos. Hopefully I can cover most of the content up to the section about Lagrangian mechanics, including interesting topics like canonical transformations, Legendre transformations, and also Poisson brackets and stuff like that. So we'll see. Okay. So first, I would like to skip section 1.1 because it's purely just examples of functionals. Okay. So we're gonna start with section 1.2. All right. So now let's talk some math. First, I would like to recall the definition of a vector space. So definition. So a vector space V over the real number R, you can change this R to other fields like the complex numbers. Is a set with two operations. Addition, which is from V cross V to V, and scalar multiplication. This is from R cross V to V, such that for any alpha beta inside R and any V and W inside V, we have the following. First is that the identity times any vector would be itself. And the second is basically associativity of scalar multiplication, basically saying that alpha times beta times V is going to equal to alpha times beta times V. And then we also have two distributivity laws, which basically says the addition of two scalars times a vector would distribute. And the same is true for distributivity on the vector side. My apologies if my audio quality is not high. I'll probably sort it out over next video. All right, so this is what defines a vector space. Also, sorry that I forgot to mention. Okay, and V is an abelian group under addition. Yeah, so this is a very important aspect. Now with the notion of a vector space, now I want to add the notion of norm to a vector space. Okay, because that's really important, right? Because we need a kind of a way to measure the distance between points, right? So the definition, a norm, which we denote using the double bar. A norm on V is a mapping from, this is from V to R, such that the following holds for any alpha inside R and for any V inside V, we have the following. The norm of V is always greater or equal to 0, and the norm of alpha times V is always equal to the absolute value of alpha times the norm of V. And then we also have the triangle inequality, so I should probably include another vector here. So the norm of V plus W is going to be less than equal to the norm of V plus the norm of W. So the last property is that if V is not equal to 0, then the norm of V is strictly positive. If not, then this is called a semi-norm. So now we're going to apply these definitions to function spaces. Okay. So remark. So recall that CAB is the space of all continuous functions defined on the interval AB. And I'm going to claim that CAB is a normed vector space with norm, the norm of F equals the maximum of the absolute value of F on the interval AB. So notice that this maximum is well defined, right? Because F is continuous on a compact set. So the maximum is achieved. All right. And you can also, most importantly, you should check that this is actually, CAB is actually a vector space, right? Why? Because the addition and subtraction of functions, they would preserve continuity as well as scalar multiplication, right? So this defines a normative space, and this notion defines a norm. And then we can also extend this to k times continuously differentiable function, right? So ck AB. So this means the function is k times continuously differentiable, right? CKAB is a normed vector space space with norm defined as the following. Norm of f is basically max on the interval AB of x of f plus the summation of all of the maximum of the derivatives up to order k. Okay, so it's going to be maximum on also the interval AB of absolute value of the ith derivative. Okay, on this interval AB. So also notice that this is a norm, and the terms in the summation, they're all semi-norms, right? So a norm plus a semi-norm is going to be a norm, and a semi-norm plus a semi-norm is still a semi-norm. All right, so now let's talk about functionals. So what is a functional? Definition: a functional J on a normed vector space V is a mapping from V to R. Of course, we can also define functionals on the space of mappings from V to the complex numbers, right? So now let's talk about continuity of a functional. Okay, so a functional is continuous at the point y inside the norm vector space V if for any epsilon larger than 0, we can find a delta larger than 0 such that for any function h inside the space V with the norm of h less than or equal to delta, we have the following. That's the difference, okay? The difference of the functional applied to the point y plus h minus the functional at the point y. So the absolute difference is less than or equal to epsilon, okay? All right. So let's also define what is a linear functional, okay? A linear functional J on V is such that, so for any alpha beta inside R, and for any y and z inside V, we have the following, that the functional applied to alpha y plus beta z equals alpha times the functional applied to y plus beta times functional applied to z. Okay, so this is basically a linear transformation, okay? All right, and so here's a remark about linear functionals. So the space of continuous linear functionals is a normed vector space. with the norm defined as following. So the norm of J equals the supremum of Y inside V of the value J applied to Y divided by the norm of Y, absolute value. Okay, so you can check that this actually defines a norm, and this is called the operator norm. Okay, and the dual space of V, and denoted by V star. Okay, we wouldn't quite use this definition, but I thought it would be nice to mention it. Also, there's a theorem that basically states that for linear functionals, boundedness is equivalent to continuity. And you can look for a proof on books like Folland's Real Analysis. Now let's talk about what it meant for a functional to be differentiable. And then we can define something called the first variation. So let's make the definition. Define, let J be a functional on V, and then fix Y inside V. Let's define delta J H to be J Y plus H minus J Y. And then we say that J is differentiable at Y if there exists a linear functional delta such that we can write this capital delta H. This is going to equal to the linear functional applied to H plus another functional epsilon times the absolute value of H. And we have epsilon go to 0 as the norm of H go to 0. The lowercase delta defined here is called the first variation of the functional J at the point Y. So this corresponds to the notion of a derivative of a function at a point, right? And you can also see if the functional J is differentiable and its first variation is bounded, then the function of J at the point Y is continuous, right? So this corresponds to the notion of saying a differentiable function at a point is continuous at that point. So now let's prove this theorem that basically states that the first variation is unique. So theorem, a differentiable functional J at point Y has unique first variation. So how do we prove this? We basically suppose that there are two ways to decompose delta j, right? And then we show that the principal linear part, they are equal. So proof, suppose we have delta jh equals this delta 1h plus epsilon 1h, which also equals delta 2h plus epsilon 2h with delta 1, delta 2 linear functionals, and epsilon 1, epsilon 2 go to 0 as the norm of h go to 0. Then we basically subtract one side from the other, and we will get the following. Delta 1h minus delta 2h equals epsilon 2 times the norm of h minus epsilon 1 times the norm of h. And then what we do is that we can divide the norm of h from two sides and define a new linear function, okay? So let's phi of h equal to delta 1h minus delta 2h. So this phi is linear. And we have 1 over the norm of h times phi h equals epsilon 2 minus epsilon 1, right? So we divide h from both sides. And actually, we can observe that since this phi is linear, we can write this as phi of h divided by the epsilon the norm of h, right? And this would go to 0 as norm of h go to 0. Hence, we can observe that phi of h for any h would equal to the norm of h times phi h divided by the norm of h. But then this would necessarily equal to 0 for any h. Why? Because we've proven that if you take h to be small, right? So if you divide this h by a large number, then both this and this will both go to 0. And that proves that this quantity would necessarily be 0 for any h. Right? So that shows why the difference between delta 1 and delta 2 is 0. Hence, we get that delta 1 equals delta 2. So the two first variations, they are equivalent. They're equal. All right. So now I'm going to talk about the extremum of a functional. So let's first define what an extremum is. Theorem. Definition. Let J be a functional on V. Then Y inside V is an extremum of J if we have the following. There exists a delta larger than 0 such that for any Z inside the ball of radius delta centered at Y, we have that Jy minus Jz has the same sign. All such z. So basically, an extremum can either be a maximum or a minimum, right? So if j is a maximum, then this quantity would always be positive. If it's a minimum, then this quantity would always be negative. So with this definition, here comes a fairly straightforward theorem. If y and v is an extremum of a differentiable functional j on v, then the first variation at the point y, so delta, is 0. So how do we prove this, right? We use contradiction. So proof, assume that this delta is not 0. Then there would exist an H in the vector space V such that apply delta to H would equal to C times the norm of H, with C being non-zero, right? So how do we get this, right? We basically, to get C, you can divide the norm of H from delta H. And the C cannot be 0 because there must exist such H, otherwise this delta functional will be the 0 functional. All right, so if we have this, we're just going to apply this to the uppercase delta H, right? So delta JH would equal to this lowercase delta H plus epsilon times the norm of H, but this also equals the norm of H times C plus epsilon. All right, so let me just say C would equal here to be delta H divided by the norm of H. All right, so what do we do here, right? Then we can take H to be less than the this radius delta. Sorry about the notation here, is a little bit confusing perhaps. So by this delta, I meant the radius delta here, okay? So we take the norm of H to be less than delta and small, such that the epsilon value of this epsilon is less than the epsilon value of C, right? Because that's possible, because when H approached 0, this epsilon would approach 0 as well. Then we can observe that this delta JH and delta J negative H would have different signs. Because why? Because this delta JH here would equal to H times C plus epsilon, whilst this delta J minus H would equal to the norm of H times minus C plus epsilon. And then these two quantities in the brackets that would have different signs. So that would result in these two quantities having different signs. Hence, you will see that this definition is violated because the extremum requires the same signs, right? So I think I'll stop for today. I still have 4 more lemmas to prove. I'll just include it in the next video. Hope you guys enjoyed the video so far. Please leave a comment if you have any suggestions. I'll see you all next time.